These are in listen-only mode.
Hello and welcome to the Great Lakes Neurotechnologies webinar series. I will be your moderator for this session. Today's webinar is Wireless EEG Setup and Analysis. As a reminder, if you have any questions during the session, please type them in the questions box on your screen. I will compile the questions and ask them to the presenter at the end of the presentation. With that, I'd like to introduce Ms. Maureen Phillips, Biomedical Product Solutions Manager, who will be presenting today.
Hi, everybody. Thanks for taking the time to join me today for our webinar regarding setup and analysis of wireless EEG data. Just to give you a quick overview, I'm going to be going through several slides just talking about some background information about EEG. I'll also go through a demonstration showing you the type of equipment that you can use to wirelessly record EEG, cover some analysis functions that you can do with the signal, and then there'll be a section at the end for questions that I'm happy to answer for you. So with that, I'm going to start sort of with a quick anatomy lesson on the brain in case maybe you don't remember. So a few structures of the brain from which you can record information include the cerebral cortex, the cerebellum, and the brainstem. What we're going to be focusing on today is the cerebral cortex. That's the region from which we record the EEG signal, the electroencephalograph. And the components of the cerebral cortex are the frontal lobe. And the frontal lobe is what controls attention, abstract thinking, behavior. It's involved in problem-solving tasks, physical reactions. The parietal lobe is another region of the brain. And this is involved with hearing, language, attention, and also spatial cognition. There's the occipital lobe, which is a small area in the rear of the brain that is really dedicated entirely to vision and visual aspects. So that includes perception, visual spatial processing, movement, and also color recognition. The fourth lobe is the temporal lobe, and that controls auditory and visual memories, language. It's also involved in some hearing and some speech. So all four of these lobes within the cortex produce tons of information, really, that we can record using the EEG. And you know, it provides a lot of important information about the electrical activity that's actually occurring in the brain while these lobes or you know, these areas of the brain perform their different functions. So what are a few methods of measuring EEG, or excuse me, measuring brain activity, or just, you know, looking at the brain in general? So there's MRI, which I'm sure many of you are familiar with, which is the use of magnetic fields to produce cross-sectional imaging of the brain. And this allows you to see cross-sectional images between brain tissues and provides a nice contrast between brain tissue and maybe abnormalities that might be occurring. There's the CAT or CT scan. This uses x-rays from several different angles around the head to produce slices, and it really is essentially slices of the brain so that you can look at very specific areas in a lot of detail. The PET scan is actually a nuclear medical imaging technique, and this creates complete three-dimensional images of the brain. So instead of just the two-dimensional images with the MRI and the CAT scans, you can see the 3D images. So then the final is the electroencephalogram, or the EEG, and that's what we're going to be focusing on today. So with the EEG, what you're doing is actually measuring the electrical activity of the cortex. And this is recorded from the scalp using metal electrodes. And I'll go into some more detail and explanation of that further in the presentation. EEG is a measure of a voltage output that results from current flows occurring between neurons in the brain. So as different neurons fire related to tasks that the brain is completing or activity, that creates an electrical output, and that's what we are measuring with EEG. So On the voltage front, the EEG signal is very, very small and actually occurs on the microvolt level. So because of this and because of the very low amplitude of the EEG signal, it must be significantly amplified in order for us to be able to see that signal and be able to derive useful information from it. So I'll talk about that amplification again a little bit later on in the presentation. So why is it important to measure EEG? There are so many applications for which EEG recording is an important area. It's an important, technique to use. So maybe it's epilepsy monitoring or diagnosis, looking at isolating and detecting areas of damage within the brain after a stroke or some kind of head injury. That's what the image on the right is depicting. Abnormal EEG signals can also be indicators of neurodegenerative diseases. That includes Parkinson's, Huntington's disease, Alzheimer's is another example. EEG can be used in the operating room to measure depth of anesthesia to make sure that patients are staying within the right level of anesthetic and not going too deep. Another application is sleep disorder detection, looking at different stages of sleep and trying to determine whether or not patients have a different type of sleep abnormality. Psychophysiology is a pretty broad application area where EEG is very commonly used in a number of different applications in evoked potential or visual evoked potential research, as well as several other, and I can talk about that a little bit further. There's also biofeedback, which is an application in which people can learn to control the actual output of different physiological signals from their body. So in addition to this, like I mentioned, there are so many other applications in which EEG is important in both clinical applications as well as research applications. So when you measure EEG, there's several different waveforms or signals that can be extracted. So I'm going to go into a little bit of detail about that now. So with EEG, different waveforms that occur are categorized by different features, and those features include the frequency at which they occur, levels of amplitude of the signal, and then also the location in the brain from which they are most commonly recorded or extracted. So the first of these waveforms is the beta wave, and this is actually the highest amplitude EEG signal that occurs within the brain. It occurs at about 13 to 30 hertz is the typical range, and this here is a frequency analysis showing that at this point in time during the recording your peaks are at about 14 and 15 hertz, and this is an actual beta wave trace showing that where the oscillations are occurring, they're at a pretty high frequency. They're occurring very rapidly. This is recorded from usually the parietal and the frontal lobe, and beta waves are indicative of awakeness and alertness. It correlates to mental activity, significant mental effort, higher states of alertness. So this is kind of what's occurring during normal daily activities when you're awake and you're alert. Interestingly and somewhat conversely, beta waves can also be found in sleep. So as your body moves through the different stages of sleep and into REM sleep, rapid eye movement sleep, that's where dreams occur. And when somebody is dreaming, it's basically the same thing as being awake almost. Your respiration increases, blood pressure can be raised, your eyes are moving very quickly, hence the name rapid eye movement. And so because your body almost thinks that it's in a state of alertness, the occurrence of beta waves will actually increase to show an increase of mental activity. So the next waveform, going down, I guess you could say, in the level of frequency are what are called alpha waves. Alpha waves occur between 8 and 13 hertz. In the frequency spectrum here you can see a peak right at about 10. The most common locations from which you can record alpha waves are the occipital and the parietal lobes. And alpha waves occur during states of relaxation while people are awake. And this is typically when somebody's eyes are closed, they're very relaxed, maybe the breathing slows slightly, the heart rate slows slightly, and then the alpha waves occur. And what's interesting about alpha waves is that while they occur at a low frequency, the amplitude of the waveform is much higher, so it can occur up to 200 microvolts. With alpha, what happens is that as a person becomes more and more relaxed, you'll see the increase in this very standard or recognizable sinusoidal waveform, which you can see down here. So that's the occurrence of alpha waves. So as a subject kind of rises out of that relaxed state, starts to become more alert and more aware when they open their eyes, that's when you'll see the amplitude of the alpha wave decrease, but you'll see the frequency of the EEG waveform increase, and that's when you'll begin to detect beta waves, which again is kind of that mental alertness waveform. The next is theta, again moving down in the level of frequency. Theta waves usually occur between 4 and 8 hertz, and the amplitude of this signal is right around 10 microvolts. That's pretty standard. It's recorded from the parietal and the temporal lobes, and theta waves typically occur during sleep. So after a patient is, the alpha waves and they're very relaxed, once they begin to fall into sleep, the very early stages of sleep, that's when theta waves will begin to occur. In addition to just sleep, theta waves can correlate to periods of emotional stress. If somebody is frustrated or upset, theta waves can become apparent. In addition, it can be used to detect different types of degenerative brain disorders. So if something like Parkinson's disease or maybe Huntington's disease is occurring, it's commonly found that there is an occurrence and an abnormality in the theta wave. The next waveform is the delta wave. This is the lowest frequency brain wave that occurs. It ranges anywhere from 0.5 to about 4 hertz, but again, similar to the alpha waveform, the amplitude of the delta wave can be quite high, all the way up to 200 microvolts. And delta waves occur at the absolute deepest level of sleep. It is the level of complete relaxation where no dreaming is occurring, and just the activity of the brain is just so slowed and so low where the frequency of the signal is, usually below 4 hertz. And so in the image here you can see the peak occurring maybe about 2.5 hertz. The occurrence of the delta wave is actually quite widespread across the brain. It doesn't occur only just in one region. It can be bilateral or unilateral in occurrence, so occurring either on the right or the left hemisphere, and it can be captured or derived from electrodes placed on several different locations of the brain. The final signal, waveform that I'll mention is what's called the gamma wave. And I was doing, some research and finding specific details about the different EEG waveforms for this presentation. And interestingly, there is a lot of differing opinion about the gamma wave. So what's known, or what is obvious, is that the gamma wave occurs usually between 25 and 100 hertz. That's the frequency of the gamma wave. The amplitude can vary depending on the person or the location from which it's being recorded. And it's actually found, or can be found, in every part of the brain. So it doesn't matter which lobe you're on, which hemisphere you're on, you can extract gamma waves really from any location on the scalp. Some research suggests that gamma waves are related to meditative states or to heightened states of consciousness. So when people are meditating, they say that they experience almost euphoric or bliss-like periods. And some research suggests that gamma waves, correlate to that. Some research has shown that gamma waves can correlate with thinking or very high-level mental processing. On the complete opposite end of the spectrum, I found research that said that gamma waves are more of just an accident. Maybe it's just a source of noise that's coming from a different area of the brain, or maybe artifact that's occurring from nearby EMG or muscle activity that's occurring. So, there is some research that states, here's the gamma wave and here's what it correlates to, and then there's other research that states, there's not much conclusive evidence to show what it really does relate to, how we know, unlike how much we know about the previous 4 waveforms. So just an example of why measuring EEG really is important, because something like the gamma wave, the more research that's done, the more that can be conclusively stated about it as to what it does or does not relate to. So when you want to record this EEG data, how do we do it? What's the standard? Some of you may be familiar with what's called the 1020 system, or the 1020 setup, and that's the image, there we go, that's the image here on the right. And with the 1020 system, it's named as such because it refers to the percent distance that each electrode is from each other in relation to the size of the head. You'll see that each one of these locations has a corresponding letter and number that indicates the region. So each letter, you'll see there's F, T, C, P, and O. Those correlate to the 4 lobes of the brain, the frontal, temporal, parietal, and occipital. And then the C actually corresponds to central. So that's just referring to the central region of the brain. The numbers actually indicate the hemisphere on which the recording is being done. So the even numbers are located on the right hemisphere, and the odd numbers are on the left. Right down the center of the head, you can see that a Z is located there in place of a number, and that's just representative of the midline of the head, since it's not really on one hemisphere or the other. The A1 and the A2 actually refer to the reference points for EEG recording. And those are typically placed on the mastoid, which is the bony portion right behind the ear. So again, that acts as your reference or your ground point. So looking at this image, that's a lot of electrodes. That's a lot of positions on the head from which we can record EEG. And one question is this all necessary? So in order to extract useful information from EEG, do you need all of these electrodes? And the answer to that for certain applications is no. Now, there are a lot of research studies going on or that have been completed where people have used hundreds of EEG channels, all the way up to 256. You can do 16, 32, 64. There's so many different configurations. But you can also extract very important and useful information from lesser numbers of electrodes. So even just from 2, 4, or 6 EEG electrodes that you're using on the head, you can grab all of the information that I previously discussed, and I'll be able to show that to you. And just to provide sort of a point of reference, a common application for EEG is sleep disorder monitoring. And the AASM, the American Academy for Sleep Medicine, has different standards set up as to what needs to be recorded for different types of sleep studies. And so for the most advanced sleep study, which does involve recording EEG, the maximum number of channels necessary is 6. So if you think about all of the information that's being extracted from the EEG signal during sleep, where sleep is being staged and according to the different levels, 1 through 4, and then also REM sleep, even things like seizure activity can be detected, looking at as somebody is falling asleep. All of that information can be extracted from just 6 electrodes placed on the head. So what I'm going to do right now is switch over so that I can show you some type of equipment that you can use to record EEG, but in a simpler way than that standard 1020 setup that I showed you there. So turn on the webcam here. Hi, everybody. The first thing that I'm going to show you is what we call the BioRadio. This is what correlates to the wireless component of recording EEG, and this is an 8-channel data acquisition device, essentially. There are 8 inputs along the front here, and that's where you would plug the electrode leads into to record the EEG. as I mentioned, EEG is a very, very small amplitude signal, and so built into the device here are amplifiers that essentially, crank up the gain on those signals in order to make them visible and viewable so that you're getting very useful information, while you're collecting your EEG data, and it's something that can be analyzed and I guess used per your particular application. So this is the device here. It can actually be worn by the subject, and it transmits data wirelessly to a Bluetooth receiver. The transmission range is about 100 to 150 feet line of sight, or the other option is that you can actually go through different rooms. So depending on the application for which you're measuring EEG, let's say it's a sleep study or maybe something during meditation, you might not want to be in the same room as the subject because it could be disruptive and affect the quality of your data. So you could be located in one room with the computer and the receiving end while the patient and the device are in another room. So it's a little bit more natural for them in order to record data. So then to set up your data acquisition, this is what we call our BioCapture software, and this allows you to record, as I mentioned, up to 8 channels of EEG, and you can configure those 8 channels on the BioRadio to really any type of configuration or any type of setup. So what you would do is first choose the number of channels from which you'd like to record, and you can just select those here. The next thing is you would choose from this drop-down the signal that you want to measure. So in addition to just being able to measure EEG, you can also record different types of physiological signals. So not all research studies will only require the EEG recording. You may need to look at EEG or respiration in response to the EEG signal. So you can do that using the BioRadio, and just by selecting the appropriate signal here, all of those parameters are set for each channel so that you can record any combination of data that you would need for your study. Once you're finished there, you can program your device. That sends all of the information back out to the BioRadio, and then once you have everything set up here, you can just click Start and start recording your data files. Since EEG is a little bit difficult maybe just to set up for a demonstration, I hope you're not too disappointed, but I won't be putting the electrodes on my head. I'm going to use this nice fancy brain here. So this will be my demonstration as to how we use sensors to collect EEG. So included with our kit are gold cup electrodes. So the first end looks just like this. It's shaped like a cup where it has the concave section on the one end. The other end is a standard no-touch connector. This is what plugs into the channels onto the BioRadio. So when you're recording EEG from the head, if you have somebody who has hair, what you would want to do is part the area on the scalp, similar to this. You would clean the area using an alcohol wipe, get rid of oils or any kind of surface dirt that might occur. And then using the gold cup electrode and conductive paste, that's how the electrode adheres to the scalp. So the first thing, once the area has been prepared, we take the paste and completely fill the cup end or the concave end of the electrode with the conductive paste, and then that just gets placed onto the head depending on the area you're recording your data. So in this example, we've got the occipital lobe right back here. So this would just stick right onto the area like that. A piece of gauze then can be placed over the electrode to adhere it and keep it in place. And this is a nice way of setting up your EEG because, again, you're just selecting the areas that are pertinent to the type of data that you want to record, and this adheres very well, so it will stay on for longer periods of time. It's even what's used for sleep studies, so you can see that they kind of have a nice duration as to how long those electrodes can stay on. So since I'm not recording anything from a real brain, I'm going to go ahead and show you some saved data that was recorded previously of EEG, and then talk about some of the different types of analysis we can do with that signal. So what you're looking at here, this is a post-processing software package we offer called VivoSense. This allows you to save data files that were recorded in BioCapture. What we're looking at here is one channel of raw EEG data. So what I talked about with the 5 different waveforms that occur, those are all kind of buried in here right now. And if we scroll through the data file, you can see that you get amplitude that occurs anywhere from plus or minus 600 microvolts. And so since the amplitudes of those different waveforms can range anywhere from 10 to 200, it's really hard to differentiate where those might be occurring. In addition, it's hard to tell the frequencies that are occurring so that you can also differentiate between the frequency components of those different waveforms. So if I drag the mouse over a certain section, I can bring up a frequency analysis of the signal. So again, looking at the raw EEG data, and I can scroll through and look at the frequencies that are occurring at different points in time during the recording. But you can see the range of frequencies here is vast, anywhere from probably 0.5 hertz, and there's a peak here at 15 hertz. You can also see there's a peak here showing some 60 hertz noise or electrical artifact that's affecting the signal. So it can be hard to derive useful information, sometimes just from a raw EEG signal. So within this software, what you can do that's a really nice feature is automatically extract the 5 different waveforms that we discussed. So just by double-clicking on these waveforms here, the software is using algorithms to extract that information as it's occurring from the raw EEG signal. So I'll change the time scale on this really quick here. So you can see as I scroll through the data, the alpha, beta, delta, gamma, and theta waves, you can see when they're occurring and when they are at a higher peak, for example. So right here is a period of little or no alpha activity, but then right here we can see that the alpha wave activity does increase. And what you can do is, just like I did before, drag over a certain area to pull up a power spectrum of the signal. And this shows, as you scroll through the data, the frequencies or the peak frequencies that are occurring at different points. And indicative of an alpha wave, you're looking at peak frequencies occurring between 8 and 13 hertz, which is really exactly what this is showing here. You can do that for all the different waveforms. Another function of the software here is you can add different annotations. So there's several reasons why annotations might be important in EEG data acquisition. First would be sleep disorder monitoring. Maybe you want to go in and you want to mark different stages of sleep that are occurring. And in order to mark those different events, again, you can just drag over the plot here, add an annotation. You can add a custom title to that, and then through an annotation manager down here at the bottom, once you've added several annotations, you can just skip from one to the next. Another reason that this function might be useful is because another common application for EEG monitoring is evoked potential research. And evoked potentials are a response that occurs in the brain after some type of external stimulus. It could be a visual stimulus like a picture or a video. It can be an auditory stimulus. It could also be a tactile stimulus, so a touch, a puff of air, something like that. And so what someone may want to look at is the response immediately occurring after that stimulus, whatever it might be. So there might be an instance where somebody is told to press a button as soon as they hear a sound, so that you can see the response time between when that sound actually occurred and when the subject was able to react to that sound. And you could add annotations for that. So evoked potential research is important for maybe just assessing hearing or sight and the reaction time it takes in order for somebody to be able to perceive those stimulus. It can also be useful for different types of disorder diagnoses. It's actually quite common when diagnosing multiple sclerosis, for example, and looking at the reaction times between presentation of a stimulus and when the brain can actually respond electrically to that stimulus. So we actually are integrating data from the BioRadio into additional software packages that allow you to, sorry about that, I don't know what that is, into different software packages that would allow you to, in a completely automated way, synchronize data that you're collecting with BioRadio with the occurrence of external stimulus, and then being able to monitor the immediate reaction to that with really complete precision timing down to the millisecond level. And that's definitely important when you're talking about EEG research and wanting that very tight time synchronization. So then jumping back to the presentation, just one or two more things to mention here. In addition to that automated software option that we offer, we also include a software development kit with BioRadio. This gives you two different ways of using data that you collect with the device. The first is that within BioCapture, you can save data files and export them to .csv format, and then import those data files into very common analysis packages, MATLAB. And by doing that, you're giving yourself the opportunity to do more custom analysis. Maybe there's additional features that you want to be able to extract from the EEG signal that can't be done with that VivoSense software, so you can do that. And this is actually an example of an EEG analysis using MATLAB. So what this is called is a joint time frequency analysis. And a joint time frequency analysis plots frequency over time, so you can see that the frequency is here, where's my mouse, on the x-axis. The time is here on the y-axis, and then the power or the amplitude of the EEG signal is identified by color. So this might also be referred to as a waterfall plot. So this gives you the opportunity, instead of just looking at amplitude over time or frequency analysis, you can look at all three components, time, frequency, and amplitude, in one window, really. So then, in addition to just exporting saved data files, you can also use our software development kit to stream data directly from the BioRadio into custom applications that you create or develop using LabVIEW or MATLAB. So we offer a really nice variety of flexible options with the BioRadio. So we're giving you wireless data acquisition for EEG, which is a great feature for a number of different studies. We provide analysis software packages if you need something that's more automated and kind of ready to go. And then we also provide the software development kit aspect to give you complete flexibility in what you may want to do with your data. So here is a list of references for my presentation, and I just want to thank everybody for your time. What I want to do now is open up the floor to any questions.
As a reminder, if you have any questions, please type them in the question box. First question, are the 8 input channels on the BioRadio limited to 8 electrodes on an EEG cap?
Yes, they are. So the inputs on the BioRadio, sorry, let me take a step back. So since the inputs or the channels for EEG are single-ended inputs, and there are 8 channels on the BioRadio, you are limited to the 8 inputs. That does not include your ground or your reference that might go on the mastoid. We already have one ground channel that's referenced to all of those 8. However, you can combine multiple BioRadios if you needed to record 16 or 32 channels, a higher number.
Okay, and in reference to the electrodes, is the paste side up or directly on the scalp?
The paste goes directly on the scalp, and what that does is create a conduction between the scalp and the electrode. And what I did when I was placing the electrode on the head was I put a large amount of paste on the side that directly adheres to the scalp, and then a little bit on the side on top just to get the gauze to stick and create a nice seal between the electrode and the head.
Okay, can you pick up alpha, beta, theta, and theta waves from just one channel?
You can. The type of waveforms that you extract are dependent on what's going on in the brain at that time. So in my previous slides I mentioned that different waveforms occur in different regions of the brain commonly, but that doesn't mean that they can't occur or be extracted from other areas. So if you have electrodes placed in the occipital lobe, you would be able to extract those different waveforms as the as somebody moves through different stages of whether you want to call it alertness or yeah, I guess alertness would be the best way of saying that. So what I showed you on the screen with the analysis software, that was one EEG electrode, and we were able to derive those 5 different waveforms from that one channel.
Okay, what is the max sampling rate per channel?
The maximum is 960 hertz, and from a lot of the reading that I've done, usual sampling rates for EEG can range anywhere from 250 to 500 hertz, so we provide ample sampling rate for that. And then if you're also looking at something like the evoked potentials, and you need something that's going to provide a very quick response time, the 960 hertz sampling rate is definitely efficient for that.
Is coherence analysis possible with your software?
It depends on whether or not you're looking for automated analysis, you know, something where you might be able to just go through and say, okay, here's a level of coherence A, here's a level of coherence B. What you would really need to do is define the parameters of coherence. You know, what are we determining, you know, how are we determining whether somebody is coherent or not? Is it an indication of alpha wave occurrence? Is it delta wave occurrence? It could be several different things, and you can then take your data file and at different points mark when those waveforms are occurring or somebody's moving in or out of beta waves to alpha waves, for example. So really you can analyze and look at anything that's occurring in the brain as long as you have your parameters set up as to what you're defining as coherence versus not.
If you want to synchronize brain activity with behavior, how easy is it to do this? With only 8 channels, how many biomeasures can be recorded off of a single device?
With the 8 channels, as I mentioned, they're programmable. So each one of those inputs can be used to record a different type of physiological signal. So if you're looking at something like behavior monitoring, there's several other signals that could be important for that type of a research study. Respiration might be important, looking at ECG and heart rate. Even something like muscle activity could be an important measure. So what you can do is configure those 8 channels on the BioRadio to be specific to that. So let's say maybe you only need 2 channels of EEG, then you can use those remaining 6 channels to record the other biopotentials and physiological signals. And you can, again, kind of mix and match depending on what you feel is necessary.
Is LabVIEW part of your software?
I'm sorry, you cut out there just a little bit, Lisa.
I apologize. Is LabVIEW part of your software?
LabVIEW is not a part of the software directly. We just provide the integration between our device or our software, data that you acquire with our software, and LabVIEW. So you would use it if you already have the LabVIEW programming language, essentially, because we don't provide the full package. It's sort of the link between our system and LabVIEW.
Okay, I think we have time for one final question. Can the channel number be increased to, say, 16 or 32 channels?
On one BioRadio device, this is the device that we offer, so you are limited to 8 channels on one, but you can collect data from multiple devices from here. So if you needed 16 or 32 channels, you can almost daisy chain multiple BioRadios together in order to do that. So it may or may not work depending on the environment that you're recording your data in. If someone is just you know, remaining kind of still and in one room, having multiple devices might not be an issue. But, you know, if you wanted them to be, let's say, in a more active environment, having 2 or 3 of these could be a little bit cumbersome. It really just depends, but that capability is definitely there.
Okay, it looks like that's all the questions we have time for. If you've asked a question and we haven't gotten to it, we will have a record of all questions asked, and Maureen will follow up with you directly to answer any questions that you have.
Thank you again, everyone, for your time. I really appreciate it. I'll be following up with all of you directly to provide a link to a recording of the session if you're interested in viewing the information one more time. And my email and phone number are right there on the screen. If you have any additional questions, feel free to contact me at any time. And I hope you all have a really nice rest of the day. Thank you.